is presented by Eric DeRose. I am the product marketing engineer for AVX SuperCapacitors. I've been with AVX now for 3 years. I'm a 2016 graduate of Alfred University. A little brief background about myself. I'm an avid sports fan and a sneaker connoisseur. As it pertains to work, I handle all of the product marketing responsibilities from the US side for supercaps. That covers pricing, data sheet responsibilities, and even some global interaction between Europe and Asia with my counterparts in those regions. For today's webinar, though, we'll be covering why batteries potentially lack in a design, how supercapacitors aid those and potentially even replace them as a whole to extend lifetime. Briefly, how and why it works to implement a supercap, and then even a small-scale concept study. I can show you some real data on how it actually lengthens battery lifetime, runtime, just design efficiencies, improvements overall. We'll briefly dive into our whole portfolio of supercaps, and then we'll finish with takeaways and we can field some comments or questions through a specially set up form that we've created. And then everybody will get this presentation following this entire webinar. So getting into some battery disadvantages, so we're going to cover, why batteries are this or that, and then we'll kind of introduce supercaps to the realm, how that's going to benefit the circuit, and then how, why, and then show you some real data again. So touching on batteries, and now you should probably already know, but to reiterate, AVX isn't a battery manufacturer, nor do we provide or sell any batteries. So don't think of us as a battery expert, but we know how to supplement the battery or combat battery deficiencies. Some initial things that stick out are always going to be, first and foremost, temperature range. So for those unfamiliar, there are pretty much two main batteries that are offered in the realm. To keep it real simple, they just call them either primary batteries. Those are non-rechargeable batteries. So if you think of going to your local drugstore, grocery store, I don't know if you have a special battery plus store that are sometimes around, but those are non-rechargeable batteries. Those are like the common AA or AAA batteries that would go in your handheld devices at home, say a TV battery, TV remote, even some consumer devices that use those, call them over-the-counter batteries. Secondary batteries are going to be rechargeable batteries. So think of lithium-ion batteries, batteries that are in your computer, in your cell phone. Those are probably the more common of the two in terms of overall worldwide uses. But in general, they both have a much slimmer temperature range, and that is pretty critical in terms of long lifetime. So when we talk about heat generation is pretty much the main culprit of any type of electronic component failing ahead of time, or when we try to generalize or dictate MTTF plot, MTBF plot, trying to, let's say, guess on, I don't want to say guess, but calculate or give an expected lifetime of a design or of a component. Temperature is usually always the main factor in terms of those failing sooner than expected. And not only are we talking about the ambient temperature of the component being used in, but the temperature of the actual component itself generating, whether that be because cycle count is too repetitive for the component to handle, or whether that just be that it's being used in a temperature range that is not recommended for. And as you can see, they're noted, and these are kind of just some general numbers you can kind of find online, but those primary batteries are pretty much bound between minus 30 on the lower end if you find a good battery, and then maybe plus 70 on the upper end, usually plus 60 or plus 50 you'll see notated around the industry. And then secondary batteries are pretty much bound between minus 20 and plus 55 degrees C temperature range. Cycle life is a huge discrepancy between batteries and what we'll introduce soon, supercaps. Batteries, for the most part, are pretty much bound with about the low thousands of cycle life. And when we say cycle life, that's the number of charges and discharges. So to give you a real world example, think of your cell phone and every time you go to sleep at night. Every time you plug in your phone, and I'm iPhone biased, so every time I plug my iPhone in at night, I am quickly degrading the lifetime of the battery. It's not a mistake as to why Apple introduced those the battery recall in which they did like the discounted battery replacement program that they did over the past couple of years. People like to think that Apple's bogging down your battery on purpose every time they do an update. That's not necessarily the truth. Really, that's just a battery characteristic. Batteries they have a limited life cycle, and that is directly seen in number of charges and discharges. In comparison, and I'll kind of get to that in a slide or two, but supercaps are far superior in cycle life. We're talking hundreds of thousands of cycles depending on the type of application. Time to recharge is a huge one, and if you look at it from the user standpoint, we would call that downtime. So let's think of a handheld drill, right? Cordless drill. So that has a battery pack, and there's, depending on how frequently you're using it, every time you lose complete power, you have to put it back on the charging station. And the world works around I need to get things done now type of mindset. So having that downtime is really it stinks, for lack of a better term. And supercaps are able to charge and discharge almost instantaneously. And then last but not least, the high internal resistance, or ESR, of batteries are they stick out like a sore thumb. So by implementing the supercap and taking advantage of that low ESR characteristics, you can definitely provide much more current, not only instantaneously, but in general, the amount of current you can provide due to low ESR. All right. So aiding the battery, we're going to implement supercaps, or other terminology in the industry. They are ultracapacitors, EDLCs, gold caps. I've seen S caps, U caps. Those are just synonyms of supercapacitors. And the biggest thing that the supercap is going to bring to the table for the battery or the design is taking on those current pulse needs of the design. So what does that do for the battery? It's less heat generated by the battery. And like we talked about, heat is a direct comparison with lifetime and lifetime degrading. It doesn't require the battery a deep depth of discharge than it would have without the supercap in the system. It's less number of recharges for the battery itself too. So when we're talking about the cycle life again, since it has a defined or a limited cycle life count compared to the supercap, less recharges, you're going to get lengthened lifetime. And then it also allows for application uses with the supercap that otherwise, without it, the battery would be either not sustainable or it would be much larger as a system. So think of it like you can size down. So say, for instance, and I'm going to use this in a real general type of way, say you have a battery that's the size of a car battery, just to give you a size in your mind, right? You have a car battery size battery, and maybe the way to improve that design is by sizing down the battery itself and then adding supercaps to the whole, the design, so that now you're taking advantage of the supercap characteristics. You're not straining the battery as much, and it's, again, overall improved efficiencies as a whole. So some implementation thoughts, things that should cross your mind when considering a supercap for the design. First and foremost, it's not just as easy as picking a supercap and saying, like, I'm going to throw this in, we're going to put it in parallel with the battery, boom, everything's going to be, all great. So it is pretty design intensive. There are multiple things you need to consider. But first and foremost, ESR is going to be the main thing when we're talking about providing current in the design. So as a rule of thumb, a general benchmark we like to use, the ESR of the supercap compared to the battery should be at or less than 25% of the battery's ESR in order to be of benefit to the design. Now, you can kind of fine tune that. We can be a little bit less. You can use a little bit higher than 25%, but general rule of thumb for sizing and in comparison, if you have, and I'll give you general numbers now, if you have a battery that has 1 ohm of ESR, you would want a supercap of ESR at 250 milliohms or less, or 0.25 ohms or less, to kind of be of use to the circuit and truly serve its purpose. When considering the multiple factors, it's really a balancing act. So you're balancing application requirements of temperature range, the number of cycles, so cycle count, space constraints, and you're even considering cost of service replacements or maintenance on the system. That's huge. Again, we don't want to just be selling something that's maybe just going to be a negligible effect, right? It's hardly any trade-off. There should be some benefit here, and that could be in cost savings. That's most of the time what it is. So, and we'll touch on that in a couple slides. And then last but not least, since it's in parallel with the battery, we also want to be mindful that we're not self-draining the battery. So the supercap has a DC leakage current rating, and that will self-drain the battery if it's too high. So again, going back to that balancing act, not only are we considering ESR, but we gotta think about leakage current as well. So I think now we're going to touch on the basics of how it works, and what we're trying to show is that not only does the supercap have the lower rated ESR there that you'll see denoted by, I've given these arbitrary numbers. They don't mean anything other than you may see typical batteries with an ESR of a 0.9 ohm rating, and you may see typical ESR ratings for supercap at a tenth of an ohm. But to go on, the supercap, due to its low ESR characteristics, can provide much more current, much more quickly. So in the real world, we're placing the supercap in parallel with the battery to absorb those repetitive current spikes or pulse power applications and provide a large amount of current for peak power assist in similar applications, of which current is the demanding factor of the design. So to kind of reiterate or kind of give a summary of this whole thing again, the supercap has much lower ESR. We're able to provide much more current in a quicker fashion, and we're lengthening the lifetime of the battery because it can hang out in steady state operation, just provide power to the system as a whole, and not take on those current hits to the design, because that's what ultimately leads to battery degradation, or why the battery may not be sufficient enough to provide the current in the application without the supercap. So I kind of told you we had a brief study, and while I'm at it, I'll give a quick shout out to Ron Demko, and he was able to do this in quick turnaround and give this a nice look for the presentation or the webinar. So I want to kind of preface here, this is a real small scale study. This isn't exactly showing doubling of life, but this is really quickly, this is something that Ron has a lab at home that he's able to kind of draw get this data for us in terms of not only webinars, but even some white papers and such, and even for customer requests. So we definitely appreciate that. So this is definitely a small scale example. And what we did is we took a 80 milliamp hour lithium polymer battery without a supercap, and that's the plot on the left. And then we did the same exact setup, 80 milliamp hour battery, lithium polymer battery, with a supercap in parallel. And we used a 1 farad Prismacap, and that is newly introduced to the market very, very soon in the next coming months here. Probably we're looking at February, March timeframe, just to give you a benchmark for those that are kind of thinking of Prismacap or may have heard it or may have not heard of it. But in general, and I'll explain Prismacap in a couple slides here. But in general, we just placed the Prismacap in parallel with the battery, and we tested it with a 10% duty cycle and a 250 milliamp load. So to kind of explain what the 10% duty cycle means to those who may be unfamiliar, 10% duty cycle is it's a 1 millisecond, think of a 1 millisecond current on and 9 milliseconds off, and then it repeats again. So it's a 10 millisecond period. So think of every 10 milliseconds, this 1 millisecond on, 9 millisecond off thing is happening continuously until we reach the 3 volt cutoff that's kind of shown in this plot here. And to show direct results, and again, this is small scale. This could be large scale if we increase the size, the farad range of the supercap, if we give a broader scale application example. But you'll see here that we've got about approximately 15,000 seconds with the supercap compared to about 13,500 seconds without the supercap. And that alone ended up, and you do the translation seconds to minutes, but it ends up being about 25 minutes longer runtime. So something super small scale. We did, this isn't Ron's setup, but think of like, do it in your garage, taking these readings. We're able to show immediate results with a supercap in parallel with a battery for something as simple as this kind of setup. And then, sky's the limit we can go larger type of applications in terms of lengthening lifetime, lengthening runtime of the system with a supercap in parallel with the battery. So in general, the approach we like to take when recommending supercaps for designs is not always completely replacing the battery. In fact, that's probably the hardest thing to do. And there's multiple reasons to that. A lot of applications that batteries serve, present day, are truly advantageous for the battery because of the energy density disparity between the two technologies present day. And that gap is slowly closing. We're getting improvements overall, and I'm talking industry-wide, in which supercaps are starting to gain more traction for energy density compared to batteries. They're still probably in the range of 10 to 1 or 8 to 1. Batteries are superior over supercaps. But for the applications in which we can nitpick and actually completely replace a battery system are not limited to, but that initially come to mind, and you'll see widely across the industry, are like pitch control in wind turbines, in data centers in which they use like rack mount designs. That's a quickly growing, call it a standard setup with supercaps. We're able to create these, call it custom modules, even though they're not so custom nowadays, with these rack mount setups, whether it be using larger cells or smaller cells, and then we can kind of use them as plug and play or Lego pieces for however many we need, wherever the voltage dictates. Energy harvesting applications. Think of energy grid systems, designs like that with solar panels or solar designs. Supercaps are able to think of hold more energy and disperse it when needed quicker, and also charge up quicker. And then some RTC applications are pretty common. For supercaps, they're usually dominated by the coin cell type, but coin cells are quickly fading away, and we're seeing a lot of designs needing to implement the cylindrical type as they're more accessible and probably at this point in time, probably even price comparably, maybe even cheaper. But in general, the supercap module, we call those modules as, these type of designs are going to require many cells in series to attain a certain working voltage usually. To meet those voltage energy density requirements, we got to justify it by lifetime extension, improve design efficiencies, the cost savings of the design and maintenance. Those all got to be considered and justified. And again, we attain those by series parallel configuration with the supercaps. Usually batteries are easier to get 700 volts in a single cell or a single setup compared to the supercap. A little bit more design intensive. So we'll touch on a little bit of our own portfolio here. This is the AVX broadening. It's an ever so broadening portfolio. It's almost on a daily basis in which I'm loading a new spec for our catalog or for a specific customer if it's a custom design. To give you a little delve into what we've got here, our oldest offering is called BestCap. It uses an aqueous-based electrolyte technology. We see capacitance range from about 5 millifarads to 1 farad in a single cell. And the cool thing about BestCap is we're able to attain a much wider voltage range in a single cell. And I mean a single cell is what you'll see there, that render there, that picture, that is a single piece. As compared to when we talk about an SCM module, those are going to be, multiple individual cells to get to 20 volts that we can get into one cell with a BestCap. It has a much slimmer temperature range. A lot of the design characteristics or attributes of BestCap isn't really suitable for nowadays applications that supercaps are being adopted on an everyday basis. So BestCap is kind of getting a little bit of a fadeaway in a sense, but it's very cool that it's our only capacitor-like supercap, in which there's no polarity dictated or indicated on the package, whereas everything else is polarity indicated. So you can use it for AC power applications or filtering where those fit. Best cap is manufactured and shipped out of Juarez, Mexico, our Juarez facility. Our SCC and SCM series parts, they are the most common that you'll see in the industry. They're, you know, the price competitive stuff, the Lego pieces in which we place so many in series or parallel combination, a lot more easier than the other technologies. Those are manufactured out of our new facility that we recently acquired. You may have seen that announcement in China. We've been working with those guys for many years now, and we've got a great relationship. We're able to control the R&D efforts, shipment control in terms of prioritize in terms of you know, expedites and such. So there, you know, a lot of positives with that acquisition, but it's nothing new, nothing changing with the portfolio. In case anybody had worries with that or what's on the horizon, is only going to be even better, and we're going to get to market even quicker. We're working on newer electrolyte, or playing around with electrolyte technologies. You know, the salt ions in there that dictate the working voltage. So, you know, next thing. We always want to increase working voltage per individual cell. That's, you know, a constant effort in the supercap industry, industry-wide. We want to always increase energy density per volume. That's always a constant effort in the industry. Those are, you know, AVX initiatives, always, constantly. But to kind of give you the overview on this technology, we span between 1 farad to 3,000 farads about per individual cell. 2 volt or 2.7 volt and 3 volt rated cells. 3 volts a little bit of more of a specialty. You don't see every manufacturer offer 3 volts. We meet the industry standards, the -40 to +85. You know, with considered voltage deratings, we can offer the pre-bent leads. That's a consumer or customer growing trend where they like to see those pre-bent leads for ease of mounting to a board. We can do some custom wire harness designs with a connector. We can do custom designs with series parallel combinations to increase working voltage and capacitance, you name it. And all that is attained usually using our SCC LE design parts. Those are low ESR design parts. Those are critical, as ESR is additive as you place so many parts in series. And then on the SCM side of things, you'll see there that kind of green pictured part at the bottom. That's what we call our high reliability SCM part. It's suitable for higher humidity applications, where humidity is another direct culprit of quickly degrading parts. You'll see ESR rise quicker, capacitance falls off as the parts heat up, heat generation. So you know, we've got, you know, data to back that, and we can get into that conversation should you want to go down that path. And then last but not least, PrismaCap, the ever so awaiting kind of hidden gem that we've been keeping up our sleeve for some time now. That is US made and manufactured here out of our corporate headquarters in Greenville, South Carolina. Lots of excitement around that. We're pretty much at the tip of the iceberg. We've been kind of troubleshooting some things, material, the manufacturing process as well. It's much more technologically inclined in terms of the way we manufacture this. It's all machine and robotic assembled. Kind of fun to see. It uses a propylene carbonate-based electrolyte technology, so slightly slimmer working voltage per part. But you know, we can walk a customer down the path of how we would implement that into your design, and you know, ways to get around the working voltage and so on. But what this brings to the table is ultra lightweight, ultra thin, low profile, and very customizable. Since I mentioned it is all machine and robotic assembled, we can kind of trim these parts in a design almost completely custom to your design and board. It could be, you know, even circular, ovular, you name it. And again, we can do one-on-ones with that should you want to talk a custom design. So you, the customer, what should be some takeaways that you think about, or what should cross your mind? Why should you implement a supercap with your design or with the battery? First things that come to mind, you're going to extend the battery lifetime when properly sized. This is pretty much a 2x or greater battery life extension. Who doesn't want to extend their battery life and see improvements on their design? I mean, it's almost a no-brainer. Of course, there's going to be some cost increases or some cost justifications to the design. We're not going to blatantly lie about that. But if it's a design where you can size down the battery, save some money on the battery, maybe you can implement the supercap at almost no cost to your final build. Or if it's a design where you're using an entire battery solution, the supercap can provide energy savings over time. So think of like money or cost savings on money spent on the energy that the battery dictates. You know, think of trying to use a word that comes to mind. It's not coming to me at the moment, but what I'm saying is utilities. That's the word I'm thinking of. Utility cost savings. That's what I was looking for. That is a cost justification. And then when we're talking about maintenance on your system, so a service guy has to go out, replace batteries, maintain battery efficiencies, or what's the word I'm thinking of, how they're battery performance on the system. There's cost expenditures there. So by implementing the supercap, you're saving on cost expenditures on service. Supercaps are a larger energy storage device, so now they're suitable for backup applications and then energy harvesting applications. That's in addition to these large-scale industrial type applications that we were kind of basing this webinar on. So slightly different kind of tune of which we would be recommending parts for that, but still applicable. Definitely a reason why you would implement the supercaps or why that should cross your mind. Again, cycle life far superior than batteries. You'd have to definitely consider how quickly you can charge and recharge with a supercap solution with and or without the battery there in the system. You can utilize the wider temp range of the supercap with your in your system by implementing that. Supercaps are definitely a wider temperature range in applications that they fit. And then the customizability of placing so many in series or parallel combinations, you're able to definitely kind of plug and play a little bit, not only more fun, but you're able to kind of control the customizability portion of it, whereas batteries are kind of more off-the-shelf type of solutions, not too much control over how much you can customize in the grand scheme of things. So I hope this was some benefit to you on behalf of AVX. We're extremely thankful for your interest in this webinar and tuning in and registering for this, and how supercaps can double battery lifetime in industrial applications. This is Eric D. Rose with AVX. I appreciate your time. Thank you so much. Hopefully we can build upon this, and this will be a segue into more of these fun webinars, and we can bridge into some more white papers and such, focusing on supercaps and using them for your designs. Appreciate it. Thank you. Have a great weekend. Happy holidays.